Now in this question, we are told that a toy is in the shape of a spinning top. You might have played with them when you were younger. In Hindi, we call them a lattu. So basically, it's just you take it, you put it on the ground, you spin it, and you see how long it will keep spinning for. So we are told that it's in the shape of a spinning top of a hemisphere surmounted by a cone. Right? Now, the hemisphere surmounted by a cone would look like this. And once again, the cone has the same radius as the hemisphere. We are told that the diameter of the base is 4 centimeters. Obviously, the diameter of the base means the diameter of the hemisphere and cone, which has been given to us as 4 centimeters. We are also told that the height of the cone is nothing but 2 centimeters. We are further informed that this toy is packaged in a cylindrical box such that the box perfectly covers the toy. It perfectly contains the toy, meaning it is a cylinder that effectively touches the toy on all sides. So it's a cylinder like this. We have been asked to find the difference in the volumes of the toy and the container. This is where you'll see our habit of not calculating right away will be of big benefit to you. So let's first get some more details about our shape. First of all, it's quite clear that the radius of the cylinder, hemisphere and cone will all be the same. Cone is on the hemisphere, in any case it's the same. And the cylinder perfectly covers the toy, which means it's pretty much the same as well. So the radius, given that the diameter is 4 centimeters, the radius is clearly 2 centimeters. Now for volume of the cone and the cylinder, I need to know the heights. The height of the cone is given to me as 2 centimeters. So let me call that small h, which is 2 centimeters. I need to know the height of the cylinder. But if we look at it carefully, the height of the cylinder will just be the height of the cone plus the radius of the hemisphere, sort of like the capsule question. So the height of the cylinder is nothing but the height of the cone plus the radius of the hemisphere, which is equal to 2 plus 2, 4 centimeters. Now they asked us to find the difference in volume of the container and the toy. The volume of the container is just the volume of the cylinder. The volume of the toy will obviously be the volume of the hemisphere plus the volume of the cone, because they're on top of each other. Total volume will be what they contain. So they've asked us to find volume of container minus volume of toy, which is equal to volume of cylinder minus, in brackets, volume of cone plus volume of hemisphere. And now let's plug in our formulas. We know that the volume of the cylinder is pi r square capital H, because in this case the heights are different, minus, in brackets, we have volume of the cone, which we know is 1 by 3 pi r square lowercase h, the height of the cone, plus the volume of the hemisphere, which we know is 2 by 3 pi r cubed. So Upon opening the bracket with the minus sign, this will become pi r square capital H minus 1 by 3 pi r square lowercase h minus 2 by 3 pi r cubed. The minus sign goes inside. This is clearly nothing but pi r square into h, because I can take pi r square common from all of them, minus h by 3, the small h by 3, minus 2 by 3 r. And now we can plug in our values. We know that, let's just leave pi as pi for now. We'll see whether we want to take it as 3.14 or 22 by 7 based on what we get. R square, radius was 2. So it will be into 2 into 2. The height of the cylinder was 4. The height of the cone was 2. And of course, the radius is also 2. So we have 4 pi into 4 into 3 would be 12, taking the LCM, minus 2 minus 4 whole upon 3. And so we have that our final formula is that it's 4 pi into 12 minus 6, so 6 by 3, which should be nothing but 2. So the answer is 8 pi. Now since 8 is not divisible by 7, we'll take it as 3.14 and the unit, which will be centimeter cubed. So here again you can see that the major benefit of not taking the values right away is I don't have to do 3 major calculations. I have to do just 1 major calculation. And so of course 8 into 3.14 will be equal to 14 into 8 is nothing but 112. So this would be 25.12 centimeter cube. Because what I did was 8 into 3 is 24, 8 into 0.14 is nothing but 1.12, so 24 plus 1.12, 25.12 centimeter cubed. This is the difference in volume of the toy and the container. So far we have looked at 3 questions in which we have shapes on top of each other in such a way that they are perfectly on top of each other. Now let's look at a question where that is no longer the case. So like I said, let us now look at a question where the shapes do not perfectly align. So we are given that a cube is such that from the top of the cube, a hemispherical depression has been cut out in such a manner, and they've given you the figure where it looks like this. So the hemisphere has been cut out in this manner from the top of the cube. We have been asked to find the volume of the remaining part of the cube as well as the total surface area of this figure, where the cube was initially a solid cube. So before we go on to it, let's make a figure of what the top of the cube looks like now. If I was looking at it from the top, the top view of the cube will be like this: a square with a circle inside it, because the base of a hemisphere is nothing but a circle. So let's again first deal with volume, because that's actually easy to deal with here, and then deal with total surface area. Now, the volume of the solid remaining will obviously just be the volume of this cube minus the volume of the hemisphere. Because if it was completely solid before and I've just cut out a hemisphere from it, that means that part is gone. So it's volume of the cube minus volume of the hemisphere. Now we were given that the radius of that the side of the cube is 7 centimeters. So logically, if the side of the cube is 7 centimeters, that also means the diameter of the hemisphere is 7 centimeters. And so from that, the side of the cube is 7 centimeters, the diameter of the hemisphere is 7 centimeters, and so the radius is 7/2 centimeters. We can say this because the circle is clearly touching the two sides of the sphere, which means the diameter is equal to the side. And so once again, from our formula, we have the volume of the cube, which would be S cube minus the volume of the hemisphere, which would be 2/3 pi r cubed. So here you can take common by observing that the side of the cube is actually just 2 times the radius of the hemisphere. So that's up to you how you want to do it. In this particular case, I'm going to put my values in and then maybe take something common. So the side of the cube, which was 7 centimeters, means the volume of the cube is 7 cubed minus 2/3 into pi into r cubed, which would be 7/2 cubed. This is nothing but, I'm not calculating it right now, 7 cube minus 2/3 into pi into 7 cube upon 2 cube, using properties of exponents. If I have a fraction to a power, I can separate them. So I can actually take 7 cube common. We left with 1 minus 2/3 into 22/7 into 1/2 cubed. And so we'll calculate this as much as we can. Obviously, 1 2 will cut with one of the 2's from the cube. Another of the 2's will cut with the 22 to make it 11. So we'll just be left with 1 cube here, 1 2 here. So we have 7 cube into 1 minus 11 upon 42, which is equal to 7 cube into 42 minus 11, 31 upon 42. Once again, 1 7 will get cancelled with the 42, leaving us with 6. So our final answer would be 49 into 31 divided by 6 centimeter cube, which you can calculate for yourself. Now let's come to the total surface area of the figure. So logically, 5 sides of the cube have been unaffected. It was solid at the bottom, it's still solid at the bottom. Solid on the 4 sides, still solid on the 4 sides. But now on top, from the top surface of the cube, the top square has got this circle cut out of it, leaving only these 4 corners. So you would be tempted to think that the surface area is now 5 sides, so 5s square, plus area of the top side minus area of the circle. But you need to add the area of the hemisphere, because when I cut out the hemisphere from my cube, the hemispherical portion exists. The surface of the hemisphere is there. It's like a spoon. A spoon has the inner surface. Something might be missing, but it's still there. The surface is still there. So the total surface area will be the 5 sides of the square plus the top side minus the circle plus the curved surface area of the hemisphere. So to make that a little bit easier, we see that the total surface area will be equal to 6 times basically the total surface area of the cube minus the surface area of the circle, or literally just the circle is removed from the cube, plus the curved surface area of the hemisphere. Because like I said, it's still there. It's like if you have a tub of ice cream and you scoop some ice cream out, the volume is gone. That circular part of the surface is gone, but a new surface has been created, the scooped surface. So obviously minus pi r square plus 2 pi r square will just be 6s square plus pi r square, which is equal to 6 times 7 square plus 22 by 7 into 7 by 2 squared. So 7 by 2 into 7 by 2. So obviously here gets cancelled, 11. So we're left with 6 into 49 plus 77 upon 2. And we will simply calculate this to get to a reasonable answer. So 6 into 49 is nothing but 294 plus 77 divided by 2 is nothing but 38.5, and so my final answer will just be 300 and let's see 32.5. And of course centimeter square. And so this is how you approach a question where it's not a perfectly covering figure. You have to use a lot of thought and very carefully come to your conclusion. When we talk about surface area in particular, all surfaces exposed count as surface area. So while the volume is not there, the surface area is there. So now let's move on to a different type of question, which is known as transformation of solids.